Second course is looking at the manufacturing triangle, where we think of cost, quality, and schedule. Start off with a pop quiz. What's the biggest challenge in manufacturing?
QC.
See, that's definitely a huge one. What I look at, and this always blows my mind, so this is back in 2004 at the Roomba line. We had about 5,000 workers. This is only a quarter of this is one of 4 floors that I'm just running with the camera. So here's about 1,200 workers. You can see different, like here's a test station, and so on.
They don't let you take those videos anymore.
No, the things have changed. These were back in definitely in the fun days. Yeah, it was amazing, and this happened so quickly. Like this is probably a year and a half into production. So when I look at it, like quality is definitely a huge challenge and has profound impact. But for me, it comes down to like communication. So if you think of when we designed the first Roomba, maybe there are 8 to 10 people on the team, some handful of people, like no more than in this room. How do you get the knowledge in all of our heads into all of these workers that don't speak English or don't speak English period, are so far away, are going to turn over 20% year on year? It just, for me, it's still mind-numbing. And if we kind of look at it, like here's Elliot Mack, the original mechanical engineer on Roomba. So Elliot sits in his office at iRobot. He designed something in those days in Pro E, packages it up, sends it over to the factory. Tooling shop gets it. They've never met Elliot, so they're trying to interpret just through the CAD database what Elliot had on his mind. They build these huge chunks of tool that weigh thousands of pounds. Those go over to these workers who have probably never met the tooling guys, and they certainly haven't met Elliot, at least on the first pass. And eventually we end up building a lot of product. Where it gets really interesting is when you start feeding that information backwards. So imagine if the tooling people, as they're putting it together, it's not going to always go together perfectly, or they're going to have some opinion on how it could be made better. And we're still working on better ways to do this. There's all sorts of great tools like GrabCAD and so on that make this easier. But getting the information to flow backwards, so Elliot, as he's designing the next part, can take that knowledge and do a more efficient thing. But yeah, the whole communication just, it's still, I've been doing it a long time, and it still boggles my mind. So we think of our manufacturing triangle, and yeah, you get to pick 2, although you always want to pick 3. And this is really targeted for consumer electronics, where you really are balancing 3. So we'll spend the rest of this talk just looking at these and breaking them down a little bit. Start with the cost of goods sold, and really this is the direct cost of what the product costs. We usually look at it in what we call the X-factory stage. You could also look at it at FOB or freight on board or landed, but for consistency, we pick X-factory. And there's a lot of variables in there. It depends on what running changes you've made. It may depend if you've got a lot of copper on the commodity price of copper, or oil if you've got a lot of resin. You know, when did you do the buy, and what have the global markets done? So it's definitely a complex moving target. Just start with a super simple retail model. So cost of goods sold is what you pay the factory for. The sell-in price, or the wholesale price, is what you sell it to a retailer for. And then the sell-through price is what a consumer would pay to it. So this is basically your profit as a company. And looking at some of the levers we have to control to reduce the cost of goods sold, because that leaves more money in your pocket, which lets you have more working capital, or bring more money home, or do more advertising, or whatever you need to do. There's basically 2 main parts: the stuff you control with your design, and then the stuff that's controlled by your manufacturing partner. The one that I'm going to highlight is pack out, which is really the accessories you put in the box and ship it. We had one, actually I will talk about the Scuba, which is this really cool floor washing robot that we put a lot of blood, sweat, and tears into building. And we ended up packing out battery chargers and cleaning brushes and virtual walls and all of this stuff. And by the time we were done, we had to retail it for about $400. And it just didn't sell at all. And what we realized is we're competing with a $10 mop and bucket. So the consumers were a lot more price sensitive than what we thought. The cheapest way to, or the easiest way to make that price go down was to pull stuff out. So don't put in all the extra charging shoe in so much. And once you get to $229, it took off like crazy. So the cheapest or the easiest way to reduce your cost of goods sold is take big stuff out and sell it as an accessory. That's always what we look at first. The other thing that's one of my personal pet peeves is the box. So we had one company we were working with that had a $50 cost of goods sold product, and the box cost $7. It was the most beautiful box you could ever imagine. It was like this origami experiment that would unfold, and I think they were shipping it direct, so people had already bought it online. Like the box wasn't needed to sell them on it, and they would just throw it out. So that's $7 that probably could have been $1, and the rest of the $6 would have stayed in their pocket. Or on the manufacturing side, there's some things that are easier to negotiate, like the factory's always going to add in extra labor costs because it's hard to measure. You can usually negotiate that down. You may be able to negotiate down their margins. And the great thing about those is you don't need to modify your design. Then as you get more detailed, you look at changing from modules to components and things like that. But that requires significantly more work and often significant certification costs. So jumping into a little bit more detail of how do we control the cost of the BOM. One is you want to break everything into the smallest possible pieces. As we were talking about in the last talk, like I don't want to know that this product costs $500. I want to know exactly what every screw, spring, piece of plastic costs, and then I can make sure I get a fair price, which I'll describe how to do in a sec. You want to separate special components, and by this I mean the way a BOM is built, the factory applies a markup against all of the material price. So it's no more effort to place a $20 component than it is to place a 1/10 of a penny component. So I don't want to pay the same markup on every one. What we'll do is for every component above a threshold, and we usually pick $1, we're going to apply a different margin. And that's a really easy way to save money. You want it to be super transparent, so no mystery meat in there. The factory will always hide a little bit of fat in every component, and they know that you probably don't have the time and effort to go through and find that. But you do all want it to be mathematically driven so that at the end of it, whatever number's on the bottom is justified by the math leading up to it. You always want to look at it at standard. So you should know what resin costs. You should know what your basic components cost to make sure that you're getting a fair price from the factory. And you want to negotiate inclusions, and this would be stuff in their margins. So does it include the fixtures or the NRE or the stencils for the circuit boards, or are those extra things? The whole point though is no mystery meat, and you want to understand things at the molecular level. You don't just want one big number. A few other strategies you can look at. No hidden formulas, as we were talking about. Everything has to be mathematically driven. And they often will push back on this, but there's no reason it shouldn't be that way. So you just have to hold firm. One way that we get them to comply is we give them the bill of materials in fill-in-the-blank format, so they have no choice. You know, they're forced to use our format. And it also, as we were talking about in the previous lecture on RFQs, it makes it easier to compare you know, across the columns. One area you can always expect to see extra fat is in the labor rate, because it's very hard to calculate. Does anybody have an idea how to calculate the labor rate?
Estimate the time it takes to do an operation and go through your assembly process. So,
Exactly.
you know, 8 seconds per op or so.
Yep. Yeah, I mean, that's awesome, and that's at the very detailed level. At a high level, sometimes we'll count the number of workers. We know they make $4 an hour, and we know how much product comes off the line, and we'll do the math to say it's roughly this. And this is always cheaper than what they're charging.
If you had the line laid out, yeah, that.
Yeah, I mean, once it's rolling.
Yeah.
Yeah, but otherwise, when you're in the earlier stage, exactly, guessing that and adding it up. And this is really high margin for them because they apply their 15% markup to the labor, so they get to double dip on that one. So you want to go after that. As you build more and more products, building a database so you can keep track of what you're paying for all the components across multiple factories and just compare that, yeah, this resistor, this transistor costs this at this factory, and is the price equivalent at another one. Ideally, if you've got the effort getting multiple vendors quoting on it, I wouldn't jump into that super early because it is twice the effort to manage 2 vendors. And it gets confusing because you're really building 2 separate products that may, if you're making running changes and things like that, you can get out of sync and it can be a nightmare. But as you get bigger, that's a really effective way. And then finally, as you get into super high volume, if you're building 1 million products a year, every penny is $10,000 on the bottom line. If you're doing lower volume stuff, it's not worth the effort to optimize. But we would go as far, like the first Roomba, for example, had a ridiculous amount of hot glue, which was an indication of a design that needs more work. But we would literally weigh the hot glue, and we knew how much hot glue cost, and negotiate how much they were charging us. That's like a bad idea on several levels, but if you have to do it, that's what it comes down to. This is just looking at a BOM. As we were talking about, it's all mathematically driven in just some of the parts. Usually we'll see the injection molded plastic followed by the purchase parts, which are like springs and screws, electrical components, consigned components, which is often a processor. Deco would be things like tampo printing, like on this hard drive, just giving it some deco. The packaging is usually the gift box, which is a pretty, hopefully not $7 box, and then the master carton is a protective outer layer that might hold a couple gifts box. You've got the labor, and ideally that assembly labor is broken down by module, so you have a better view as to where it's going. And then the CMs, profit, overhead, and scrap, which is usually encapsulated in one number, and that's typically 15%. And then the overland transportation, you get it from the factory's loading dock to the container yard. So we'll take a look at how to calculate the cost of a plastic. So I've got a gear over here, and this is kind of a trick question. Does it matter that it's a gear? And it's tricky in that in some ways you could say it does. It's a complex piece of geometry. But in other ways, you look at it, it's just a certain weight of plastic that's going to have a certain amount of time to mold, and it shouldn't incur an extra cost. The answer is kind of between the two of them. So there's basically 3 components here. One is the material cost, which is just simply the weight of the part times the cost of the material. So that the fact that it's a gear does impact that, in that you're probably going to use a more expensive resin that has a lower coefficient of friction, like some form of POM or Delrin. The second is the overhead of running the machine, which is the mold, which will go and form the part. And again, the molding cycle time is usually not dependent on the geometry of the part. But because it's gear, you probably want to cool it a little bit more slowly, so it may be a little bit of a slower process. And also, I'm sorry, on the material cost, typically a gear will have multiple gates coming in, so there's more plumbing to get the resin in, so it doesn't tend to shrink as much. But you've got those 2 parts, you add them up and then multiply by the usual markup, and that gives you the cost of the gear. So the total part cost works out like this, just adding the material cost plus the overhead cost of the machine, plus the markup. So as an example, if the material cost was 50 cents, the overhead cost was 50 cents, and the markup was 15%, the ex-factory price would be $1.15. These are some basic resin prices from Hong Kong. You can go to this website. They're just a commodity, and it will tell you what they are for common consumer-grade resins. So in terms of if you have a gear and you want to calculate the cost, you can go to the previous website to figure out what your resin cost is and estimate that. And then these are just some rough molding costs based on the tonnage of the mold. For most gears, you could probably run it on an 80-ton mold, which is roughly $5 an hour. And you could try to figure out what your cycle time is. You're probably looking for a gear at 45 seconds to a minute cycle time. For electrical costs, it's super simple. You just take the cost of the component and multiply by the number of components, which we call usage. And so we talked about for components above a certain threshold, we usually use $1. You want to separate those, which is just a simple Excel formula, and apply a different markup, which we call the special markup. These are some standard factory markups. So just doing straightforward bare printed circuit board assemblies, which would be the PCB is the bare fiberglass board, and then the assembly is with the components installed. We'd usually see 6 to 8% markup applied to the material costs. Toys 12%, where we live in consumer about 15%, and then medical can be 40% on up. And that can get multiple times. We've seen a blood warmer that probably cost $1 in materials sold for $10 or more. So the factories there are often making super high margins. And some other costs we see in the bill of materials. So deco is, or tampo is, this is what we call tampo, basically pad printing to provide some labels. Painting is self-explanatory. Labor, it does vary every year, and it does tend to go up 20% every year. We usually see about $4 an hour right now. Packaging, as we talked about, is not only the gift pack, but you also have to include the master carton. And the idea of the master carton is it protects the gift box from getting scuffed up as you transport it. And also, if you're building, a product about this big, you don't want to load 100,000 of these into a 40-foot HQ container. It would just be a nightmare when you open the door. So instead, you have a master carton where you might pack 12 or 24 of them, and it makes it a lot easier to handle. But that has a cost with it, which you have to capture. This is a super compressed version of the BOM, but as we talked about, you've got plastic, purchased components. You might have some die casting, the electronics. You get labor down here, and then these are the transportation costs. And it's all mathematically driven, so there's no mystery meat in there. So that's the costing side. If we go back to our triangle, we got cost, quality, and schedule. The other two are a little bit more straightforward. For schedule, and a lot of what we do is consumer products. Many consumer products are driven by Christmas. Christmas has a fixed date. If you miss Christmas, you lose a significant portion of your revenue, which is one of the things we learned the hard way when we were doing My Real Baby with Hasbro and iRobot. It was our first time through, and it took us longer and longer than we anticipated. We were writing our own software language from scratch. Fortunately, we had Rod Brooks, who's pretty good at that stuff. But we should have launched in September, and we didn't get out until after Thanksgiving. And as a result, the sales are usually exponential. The later you are, you start losing the long bars of your revenue. So it can be devastating, and Christmas only happens, or the Christmas season only happens once a year. So being late can be totally devastating. You always want to have contingency in your schedule, because things never go as well as you think they might. We're a huge fan of having an on-site presence wherever your factory is, if it's in the US, Mexico, China. It's just really difficult to manage factories for anything complex if you don't have feet on the ground. And then you want to track your schedule super carefully. So you've got many discrete milestones, and you know if you're on track or not. And if you're not on track, you have to take corrective action quickly. Hope is not a strategy. And also, you always want to avoid the strategy that there's never time to do it right the first time, but there's always time to do it twice. Because you're playing with pretty big stakes. This is just a quick road to production from the prototype to picking a factory and handing over the design, creating the tools. The first shot is when the plastic comes out of the mold. Engineering pilot 1, or EP1, is when you combined and assemble the boards and the plastic. All the way through to FEP, or final engineering pilot, which is when you have a saleable product built by a skilled team of engineers in the back room. And then you get into production pilot, or PP, which was when you take it from the back room onto the production lines and figure out how to set up your floor. And then after that, you have production start, where you start throwing the big switch, and then onboard ship, where you start filling up a container. So there's a lot of steps along the way. And if you break it down even more, and the stuff just goes forever, there's many more detailed steps after that. So that's the schedule. The last part is quality. Does anybody know who this guy is?
Toshiba?
Yeah, you don't want to be that guy. It's a key thing. So he's the head of Toyota when there's all the recall problems, explaining why there's a problem. So quality is incredibly important, and it's often not sexy or the thing that you think about first. I know when we were doing the first room, but all we cared about is engineering. Like, nobody knew what quality was. We didn't know that we needed to care. We just had to get the engineering done. And we got super lucky so many times. But after that, we caught on really quickly that quality will make or break a company. And for me, it all comes down to the bottom line, is that you're going to go and you and the factory will build this product. You'll have a lot of products sitting on the loading dock. It could be tens of thousands of units. And you'll get the email or have to answer the question, do you accept the goods or not? It's a very, very simple question with a complex answer. If you accept them, then they're going to leave China or wherever you are, and they're not coming back. It's very difficult. They're going to go into the market, and if they do come back, it's going to be super expensive. So you want to get it right, But if you don't accept them, then are you going to rework them? Are you going to miss your schedule? Because that's one of the key constraints, and how are you going to deal with that? So quality is all about, being able to answer that question with confidence. Are they good or are they not good? And how do you know? And what we find is the best way to do it is not a final random inspection where you might do like a mil-spec 105 AQL analysis of statistically sampling them and be like, oh, these passed, these didn't, we're okay. You could do that, but it's there's always going to be holes in your net because you don't know exactly what to test for. What we like to do is look and be involved in the whole birthing process of the production of the entire product. So by having feet on the ground, you see, is there a new worker that got introduced to the line, or is this one worker struggling to put the part together? Whereas you imagine if you're not on the floor, you just have no visibility to what's going on or how things are changing. And there's many plans you can put together, from functional test, abuse test, transportation test, to make sure the product isn't damaged, temperature and humidity test, repetitive motion test. So if you have a button, can it pass 5,000 presses? We're looking at the Roomba bumper, based on, I think it's one hit every 10 seconds. The bumper has to go for millions of cycles over the course of its life. Mechanical switches can't survive that. You need an optical switch. So how do you do that, and how do you test for that? Because it takes a really long time to get a million hits. So factoring all of this stuff in has just got to be a really critical part, and will absolutely make or break a company. But yeah, quality is super important and merits, as you get into it, like a much deeper discussion. But it's something to plan for and be very rigorous about.